Hello everyone, welcome back to Electronics 1. In the last lecture we explored the reasoning for the diode forward current with an applied forward voltage, and this class I'd like to dig in to derive the actual magnitude of that current for forward bias conditions. Okay, so there's a fair bit of derivation involved, and let's just remind ourselves of the background here. When we apply a forward bias, we get a drop in the effective junction potential, and this results in an increase in majority carrier diffusion. Okay, so for this derivation we're going to focus on electrons. So we're going to just look at the electrons that are being injected into the p-type material. So if we look at focus at the edge of the depletion region, that location we will call XP, right? We know that there is some concentration of minority carriers with zero bias that are a result of thermal generation. Okay, but with the addition of a forward bias, we get electrons being injected from due to diffusion across the depletion region due to that effective drop in junction potential, and at the edge of the depletion region we say that the concentration of electrons in the p-type material, we define that as n subscript p at xp, right? And this area in here is defining the excess electrons that exist as a result of that minority carrier injection due to the increased diffusion current. Okay. However, we notice that the concentration of the electrons decays as we move away from the junction, and this is a result of recombination. Okay, so some of those injected electrons, as they move away from the junction, are going to recombine with holes and effectively disappear as charge carriers. Okay, so we looked earlier at the concentration of the electrons in the p-type region, at that location XP, which, as shown in the diagram here, is at the edge of the depletion region. Oops. Right, this area here being the depletion region, and I'm just showing one side of it. And that concentration, we said, is equal to the concentration with zero bias times e to the VF, the forward voltage divided by the thermal voltage. And although we didn't mention this earlier, this expression is known as the law of the junction. Okay, so it's relating the forward bias that's applied across that junction and reduces that junction potential to the concentration of minority carriers at the edge of that junction. And as also shown on the diagram, as the injected minority carriers diffuse away from the junction, and of course they're going to want to diffuse away due to that concentration gradient. Oops. The concentration as they diffuse away is going to drop due to recombination. Okay, the distance time constant, so if we relate the recombination to a length or a distance, so that distance time constant associated with this recombination is known as the diffusion length. L subscript n. Okay, so let's revisit the diffusion current again, so and use this on our path to figuring out what the terminal current is. So the magnitude of the diffusion current, as we looked at before, which is based on Fick's first law, we found that diffusion current is equal to our fundamental unit of charge, the diffusion constant for electrons, and the concentration gradient of minority carriers. Okay. So again, we presented these back some time ago, but we'll just remind us what these are. Excess minority carrier concentration gradient. Okay, so this is what's shown in the diagram here, is this gradient that's shown with the green line, or the axis really is what's hashed in cross-hatched in red there. Okay, so that gradient's going to result in some diffusion current, and you'll note that the negative sign here we've removed here for, we know we're talking about movement of electrons, and we haven't put a negative sign here, but the negative sign cancelled with the negative charge of the electron. Okay. Okay, so we can describe the excess minority carrier concentration is as a function of x here. We're assuming that our x-axis being this being our x-axis here. That concentration as a function of x is equal to my concentration at the edge of the depletion region minus my unbiased concentration, or my zero bias concentration, times an exponential term that is e to the minus x minus xp divided by my diffusion length. Okay, so this exponential term is describing the decrease due to recombination. Okay, so if you accept that concentration, minority carrier concentration expression is true, we can get a minority carrier concentration gradient by taking the derivative of that expression, and the derivative of that becomes 1 over my diffusion length times my concentration at the edge minus my unbiased concentration times e to the minus x over x at minus x at the edge over my diffusion length. Okay, I'm going to substitute in the equation for my concentration at the edge, which we'll remember is my unbiased concentration times e to the forward voltage divided by Vt, okay, minus, and my concentration when it's not biased times e to the minus x minus xp over my diffusion length. Okay, I can factor out my unbiased concentration. This is the concentration that's due to thermal generation. So if I factor that out, I get an expression that looks like this. Okay, so this is my concentration gradient of minority carriers, in this case electrons, in my p-type material. So if I take this expression and substitute it back into this expression, I get a current density. So substituting this into my current density expression, I get current density that is minus Q times my diffusion constant times my divided by my diffusion length times my thermally generated concentration, or my unbiased concentration, times e to the forward voltage divided by Vt minus 1, and this all e to the minus x for xp times the length of n. Or my diffusion length. Okay, now the electrons, as we stated in the last lecture, are going to be supplied by the external circuit in such a way to keep this current density at this level at the edge of the depletion region, at the level where x is equal to xp, right? So, or in other words, at the site of minority carrier injection, right? Again, just at the edge of the depletion region. So if we evaluate the current density at that edge and accept that that current density is the current that's being injected by the external circuit, then we can define my current density as the current density at the terminals is equal to this current density when x is equal to xp, so at the edge. So at that point, the current, this exponential term will be to a power of e to the minus 0 over ln, so the whole term drops to 1 because x and xp are equal. So I end up with a terminal current to maintain that current density at the edge that's equal to minus q over my diffusion constant divided by my diffusion length times my thermally generated minority carrier concentration times e to the Vf over Vt minus 1. Okay, the minority carrier concentration, we will remember, is equal to my intrinsic concentration squared divided by my concentration of my acceptor atoms, at least in the p-type material. So then my current density expression becomes minus q over my diffusion constant divided by my diffusion length times my intrinsic concentration divided by my acceptor concentration times e to the Vf over Vt minus 1. Okay? And to switch this to current, we can just multiply the expression by the area. So that rather than having a current density, we can get a current. So multiplying by area, in this case, it's going to be the junction area, the actual surface area of that junction. So we get an expression for current that looks like this. Okay, so to this point we've only considered the current flow due to electrons, so we can extend all these same derivation concepts to include holes as well. So, and holes, and we could come up with an expression for holes. So let's just say by similar analysis in the N region, the whole terminal current is going to have essentially the exact same expression looks like this. So my diffusion constant for holes, of course, instead, my diffusion length for the holes, my intrinsic concentration squared divided by now my concentration of donor atoms times e to the Vf over Vt minus 1. Okay, the total current is going to be the sum of the current due to holes and electrons. So the total forward current of the diode is the sum of the current due to the holes plus, and I'm going to take the absolute value of this because although we defined the our derivation showed that the electron current was negative, well, by conventional current terms it's actually in the opposite direction, so the two negatives would cancel, so we can just sum these directly and we get a total diode current that's A times my fundamental unit of charge times my intrinsic concentration, so I've just factored those out of the two expressions, times my diffusion constant for my electrons divided by my diffusion length for electrons, divided by also my concentration of acceptor atoms. So that's the component due to diffusion of holes, of electrons. Due to diffusion of holes, we have the diffusion constant for holes, the diffusion length for holes, and my concentration of donor atoms times, again, e to the Vf over Vt minus 1. Okay? We don't tend to define our currents with this level of detail, and we lump all of this component into what we call our saturation or scale current. Okay, and we see that scale current is a factor of many things, our diffusion constant, our diffusion length, our doping levels, and also the area. And we're going to come back to talk about the impact of area on our diode current here in a little bit in the future. The only term that's now missing from what we've defined as our expression for calculating diode current is our ideality factor. So the ideality factor N gets added to the expression to compensate for any recombination that occurs in the depletion region. So if we were to assume that no recombination occurs, that's when we set n equal to 1. And the expression becomes exactly what we have derived above. Okay, so a bit of work to derive that diode current of a forward bias diode, but I think it's interesting to see the origin of that current.